Hey guys, welcome to the lecture series of Elementary Classical Mechanics, where we embark our journey from basic to advanced physics. This is lecture number 5 on kinematic equations of motions in 1D motion. In the last lecture, we have learnt about velocity and acceleration. In this lecture, we are going to learn about the three main kinematic equations: derivation of first equation, derivation of second equation, derivation of third equation. Significance of kinematic equation. Without further ado, let's get started. In the acceleration lecture, we solved a problem and studied the situation in a graphical fashion. There we deduced for a linear velocity's graphical nature, we get a constant acceleration. In this lecture, we are going to learn about kinematic equations of motion which are based on constant acceleration. These equations will help us to figure out the various measurable physical quantities such as position, displacement, velocity, acceleration, and time. Equation of motion, as the name suggests, motion which are guided by the equations. Really, if we think about it, our every physical movement is guided by the equations. Not that we mention, but they are also complicated, nevertheless, they make our life easier. But now we are just dealing with one dimensional motion. Here are three equations of motion for 1D motion. Final velocity Vf equals to initial velocity Vi plus acceleration a multiplied by time t. Xf, final position equals to xi initial position plus Vi t plus half of at squared. And Vf squared equals to Vi squared plus 2a into x minus x0. For simplicity, we use V instead of Vf and U instead of Vi and xf by x and xi by x0. Now let us derive the equations one by one. In the previous lecture, we differentiated between instantaneous and average acceleration. But when acceleration is constant, then instantaneous acceleration is equal to average acceleration. So we know that mathematical form of average acceleration is delta v upon delta t. We can also write them in the form of initial and final form of velocity and time. Now we assume that the body starts from rest. Therefore, from time ti equals to 0 to final time tf. Let us make it just t. So we use this form for further process. Now we have a constant acceleration equals to v minus u upon t. We rearrange this equation in the form of v such that transforming the time t and the initial velocity u to the left hand side. Finally, we get v final velocity equals to u initial velocity plus acceleration a multiplied by time t. This is the first most one of the important equation. If you observe the equation, there is no position and we might get into trouble if we need to find the position. Thus, the next equation. For the second equation of motion, we use average velocity. Average velocity is equal to x final position minus x0 initial position upon time t. And at the initial position, the initial time is 0. Rearranging this equation, we get x equals to x0 plus average velocity v multiplied by t. Now we will save this equation for further use. Now we know that we get constant acceleration. You should have linear nature of velocity, and that linearity nature, object starting from time equals to 0, we can write the average velocity as sum of initial and final velocity divided by 2. We know that the first equation of motion is v equals to u plus a into t. So let us substitute that v into this equation. Then after applying the algebra, we get average velocity equals to u plus half of acceleration a into time t. So this obtained average velocity, we put it into our obtained position equation and we finally get x equals to x0 plus ut plus half of at squared. This is second kinematic equation of motion. Now we create a relationship between final and initial velocity with position. Thus, let us proceed for the third kinematic equation of motion. Now we need to derive v squared equals to u squared plus 2a into x minus x0. You can see this equation, the variable t is missing. So that we do is use the first kinematic equation in the form of time and substitute in the second kinematic equation. After substituting, the equation become a little crowded. You can now cancel the acceleration, find the square of initial and final velocity. See, during solving 2uv gets cancelled and you will just remain with x equals to x0 plus v squared minus u squared divided by 2a. After rearranging, you will get the expected equation. This is third kinematic equation. Let us see how much these equations are significant to us. Note that these equations are valid only when the acceleration is constant. If acceleration is changing with time, then these equations are no longer valid, like this or like this. Now to the significance. The first equation missing unknown is position. So that when position is not provided, we can be able to predict the velocity or time or acceleration, provided unknown value. From this equation, you can find the position, acceleration or time without final velocity. In the third kinematic equation, you can find these quantities without given time. Individually, this equation may look trivial to you, but combined use of this equation will lead us to many predictions just by giving initial conditions. These equations are very useful for solving problems in mechanics. You can predict the two-dimensional projectile motion by using these equations. Soon I will prepare lecture on that after scalar and vector lesson. You can follow me on Facebook and Instagram. If you want more of my lectures, subscribe the channel. Give thumbs up if you like this video. Your support will encourage me to work harder and better. Till then, stay tuned.